Good morning, students. Today we'll discuss direct form 1 realization and we'll solve a problem. Yesterday, last class, we saw that the basic structure of a direct form 1 and direct form 2. So, today we'll solve a problem on direct form 1 structure. So, we'll solve a problem on direct form 1 realization. So just we'll take an same example, the final thing last time what we took. We'll take this h of z is equal to 3 plus 4 z raised to minus 2 minus 2 z raised to minus 5 divided by 1 plus 3 z raised to minus 1 plus 5 z raised to minus 2 plus 4 z raised to minus 4. So this is the equation what we have. To this we have to find the direct form realization. Fine. So basically first to identify which is the highest polynomial what we are having here, and the numerator and denominator. So as I told you, so the numerator is nothing but all zeros. This comprises of all zero systems, and this is nothing but your all whole system. So whenever you want to write a direct form 1 towards your left hand side, okay, left hand side you have to write the zero system, and it should face in this direction. That means in the forward direction. Okay, it should be in forward direction. So whenever you write a block diagram, all zeros should be in forward direction. All zero system should be in forward direction, and the pole system will be in reverse direction. This will be in reverse direction. So hence whatever the equation we have here, so the equations will get flipped here. That means if you have a plus 3, it becomes minus 3 in the block diagram. So let's start with this. So first we have x of n. We'll see the all zero systems now. First you give an input x of n. X of n is my input. I'm taking it. So it's given 2 and 3 constant. So you can write it 3 over here like this, or you can also put an you can use a symbol also for that. So it is giving to the plus, just you add it to a plus and you leave it here. So the next one we have is identify how many delay blocks we need. We need 2 delay blocks, that is z raised to minus 2 and z raised to minus 5. So you need 2 delay blocks. As you take first delay blocks z raised to 1, and you take another delay blocks, name it as z raised to 1 minus 1. So and you add these two, you get a 2 delay blocks over here. So the first delay block is multiplied with a multiplier 4. So just this multiplier, you put a multiplier here and give it as a, I mean to say it is 4. Right, it's been multiplied with 4. The first delay block is multiplied with 4. Now you go to the second, and it's given to where? It's given to a summer here. So put it a summer over there, right? And then you come to the second delay block. Second delay block is multiplied with minus 2. So is it not? You have a constant over here 2. This is my second delay block. Take this and give one multiplier. This is minus 2, and it's given to the summing amplifier. Now just you connect all the sums over here, summing amplifier, and this will be taken out to the denominator, that is all pole system. Now this block gives your zero system. Now the zero system is get ready, it's got ready now over here. Now you concentrate on the zero system. As I told, all the multipliers should be, this is also a multiplier, you can take like this, or you can also denote it by like this, or you can put a block like this. Both are same for multiplier, so that's why I'm using two things over here. So now this thing is given, now this is connected to where? Here, to the whole system. So now you have to write a block for this. Fine. So first you make a block here, that is nothing but here one is connected to the plus. Just you write down this again, you can leave it here. Now what happens, this should, as showed here, the arrow mark, it should be in the opposite direction, all reverse here. I told no, reverse, it should come in reverse direction. Whatever the multiplier or the symbol direction should come in reverse direction. Hence we are flipping the signs here. Since it's in negative direction, we have to flip all the signs in the pole systems. So for that, first what I have a identify the delays. How many delays we have? We have a 3 delays. So you write all 3 delays here. Delay 1, fine, delay 2 and delay 3, right? So we'll see one by one. Just to give it as z raised to 1, z raised to 1, z raised to 1. This 3 is known as, you have a 3 delay over here, and you have a 3 delays in the denominator. First I identified my delay blocks. Later you see the multipliers. So for the first delay block, and I have a 1 here, so you can show it in this direction. The 1 is here, so 1 is 1 plus, it's coming over here. You can denote it as 1 over here, right? And then I have a 4 delays here, 3 delays, right? And it should face it in this direction. So now I have first delay here, it's been given to 3. Since the sign is plus 3 here, but you have to flip the sign, as I told, it will become minus 3, and it should be given to the summing amplifier, right? And I have a second delay. Second delay is multiplied with what? Plus 5. So give it to the summer and then make it as plus 5. So if you flip that, it becomes minus 5. And then ultimately you have a third delay. Third delay, you write neatly delay like this and give it to a summer. So this is having what? Plus 4, that is nothing but minus 4. Now just you connect all the summers. Okay, so finally you take your output y of, and this is your input x of n, this is your output y of n. So now you have a numerator, that is all zeros over here. You have a denominator, all pole system in the right hand side. It should come in the opposite direction like this, and reverse. The direction should be reverse for a pole, and this it should be a in forward direction. So here hence you don't have any sign difference, but here you have a sign difference over there.